Imagine you run a delivery company and you need to place one new warehouse to serve 5 existing stores. You know exactly where each store is, you have their coordinates on a map, you know how many deliveries per week go to each store, and you want to minimize your total weekly travel distance. Where do you put the warehouse? This is a continuous space location problem. And today we're going to solve it using 2 methods. The median method, which gives us mathematically optimal location, and the contour line method, which helps us visualize the cost landscape when the optimal point isn't feasible. In discrete location problems, we pick from a fixed list of candidate sites. In continuous space problems, the facility can go anywhere on a 2-dimensional plane. Any x and y coordinate is a valid point. The obvious disadvantage is that the mathematically optimal point might land in the middle of a lake or in a zone where building is prohibited. But that's okay. Continuous models gives us the best possible starting point, and then we find the nearest feasible location. The sole factor we're optimizing in these models is transportation cost, specifically the weighted distance between the new facility and all the existing facilities. The weight associated with each existing facility represents the volume of interaction, trips per day, units per week, whatever the relevant metric is. But before we can minimize distance, we need to define what distance means. In facility location, the most common metric is rectilinear distance, also called Manhattan distance. For example, instead of measuring a straight line distance, rectilinear distance measures movement along a grid, horizontally and vertically only, like navigating city blocks. So instead of going, for example, from this point to this point in this line, in the rectilinear method, we would go 1 here, 1 here, 1 here, 1 here, 1 here, until we are at the distance. The formula is simple. It is x minus a, absolute value, plus absolute value of y minus b. This is what our distance would equal. Where x and y is the new facility location, and a and b is an existing facility's coordinates. Why use this instead of straight line Euclidean distance? Because in real logistics, vehicles travel on road networks, not through buildings. Rectilinear distance is much better approximation of actual road travel in urban environments. Now, the median method finds the optimal location for a single facility when we're using rectilinear distance. The key insight is that x and y coordinates can be solved independently. We want to minimize the total weighted distance, the sum over all the existing facilities, I of Wi, times the rectilinear distance from the new facility to facility I. Because rectilinear distance splits x and y components, we can minimize the x part and y's part separately. Here is the 4-step procedure. Step 1. List all existing facilities sorted by their x coordinates. That's step 1. Step 2. Calculate the cumulative weight as you go down the list. Find the facility where the cumulative weight first reaches or exceeds half of the total weight. The facility's x coordinate is your optimal x. Now, step 3. Repeat the same process for your y coordinates. Sort by y. Find where the cumulative weight first reaches the half total. That's your optimal y. Step 4. The optimal location is the pair of x and y you found in steps 2 and 3. These might come from 2 existing facilities. That's perfectly fine. Now, let's talk about why this works. Think of it this way. If you place a facility to the left of a weighted median, more than half of your demand is pulling it to the right. If you place it to the right, more than half is pulling to the left. The median is the equilibrium point where the pulling forces balance. This is exactly to the median in statistics. It minimizes the sum of absolute deviations, not squared deviations. And that's exactly what we're doing here with the weighted distance. .5. Once we pass that 12.5 at 17, we stop and we pick 5 as our x. Now we do the same for the y. First we have 5. 5 plus 6 is 11. And then 11 plus 4 is 15. Since 15 is greater than 12, we stop. And now we have found our y star, which is 4. So the optimal location, in this case, our x star and our y star, would be equal to 5, 4. Now, what if the optimal location 5, 4 is not feasible? Maybe there's a building there or a regulatory zone that prohibits our facility. This is where contour line becomes useful. A contour line or isocost line connects all points in the plane that give you the same total cost. Think of it like a topographic map. The center is the cheapest location, and as you move forward, cost increases. The key property, every point on a given contour line has the same total cost. So if the optimal point is blocked, you simply move to the nearest feasible point on the next contour line outward. The key property, every point on a given contour line has the same total cost. So, how do you draw the contour lines? The slope of each contour segment is determined by the net weight gradient. How much total weight is pulling in each direction by any given point. In practice, if you have 2 or 3 feasible alternative sites, you calculate the weighted distance at each and pick one with the lowest value. The contour map tells you at a glance which direction cost increases the fastest. So, let's recap. Continuous space location models find the optimal facility location anywhere on a plane, not just a fixed list of candidates. Rectilinear distance, the sum of horizontal and vertical distances, is the right metric when facilities move on road networks rather than straight lines. The median method gives us the optimal location by finding the weighted median of x and y coordinates independently. And the contour line method helps us when the optimal point is not feasible. We shall proceed by solving this question. So, a logistics company needs to place one new distribution hub to serve for existing city depots. The depots have the following coordinates and weekly delivery volumes. Use the median method to find the optimal location for the hub. Here are our coordinates with the weekly trips. So, we first try and find our x. We look at the cumulative weight. So first, this would be 3. 3 plus 9 is 12. 12 plus 17, 7 is 19. 19 plus 5 is 24. Our half weight in this instance, I forgot to calculate the total weight. Our total weight would be 3 plus 7 plus 5 plus 9, which we got from here, which would be 24. So our half weight would be 12. So in this instance, this is the point where it's equal to, greater than or equal to 12. So here we stop. So we have found our x star, which would be 3 in this instance. Now we look at our y coordinates. For 9, first one is our 9. 9 plus 7 is 16. 16 is greater than or equal to 12. So therefore you stop. And our y star is equal to 3. Therefore our x star and our y star are equal to 3 and 3. Now, we have to find the optimal location. So we calculate the total weighted distance to verify it. We look at f, 3, and 3. We plug it into the formula. 3 times the absolute plus 3 minus 8 plus 7 times 3 minus 5 plus 3 minus 3 plus 5 times absolute variable 3 minus 8 plus the absolute of 3 minus 6, continuation to here, plus 9 times absolute variable of 3 plus 3 plus 3 minus 2. This would give us 3 times 1 plus 5 plus 7 times 2 plus 0 plus 5 times 5 plus 3 plus 9 times 0 plus 1. Which in the end would give us 81. So our total weighted distance at optimal location would be equal to 81. Notice that x star came from the depot D and y star came from depot B. These are two different depots. This is completely normal in the median method. Also notice depot D has the highest weight, 9, and depot B has the second highest weight, which is 7. This meant the method naturally gravitates towards the heaviest demand points. Thank you for